Right. Okay. So last time we were looking at this method based on exchangeable pair. So the method of Stein's method and due to sort of strategy. So what we did last, we set up the whole method, and so what an exchangeable pair is essentially the same thing as two consecutive samples from a reversible Markov chain, stationary and reversible Markov chain. Then we're trying to see what kind of concentration inequalities we can get out of this, and the whole so the underlying thing in Challenges method was to construct two things. One was the exchangeable pair itself, some exchangeable pair, and for that exchangeable pair there was some another requirement. So there had to be a function which is antisymmetric, like a bivariate function which is antisymmetric, and such that if you fix the first coordinate and take expectation of the second one, then the condition expectation is the function for which you're trying to prove concentration. With this and one more condition, which was this size function or something. So mu of x was defined to be half of the conditional expectation of the product of the absolute value. So fx minus xy you sample from the exchangeable pair, and you look at fx minus fy times the function that equals to tx, and you take the absolute value of this and take the conditional expectation with x fixed. And if this quantity is always less than or equal to c, then this is then we have quantitative. I think we did not prove it. We'll prove this. And then we started to get an application. And the application was with some weakly dependent random variables. So the idea was that we have some distribution in the product space. It's not a product distribution. It's not a product distribution, and it has some kind. The dependencies are weak in the following sense that if you fix all the coordinates, so except for the ith coordinate for any I, you fix the ith, if you extract the ith coordinate, fix all the other coordinates, two different settings, x minus I and y minus I. Then if you after that, if you look at so after that, if you look at this the total variation distance on the induced distribution on the ith coordinate, then that has is bounded above by some kind of a linear form. So it's like, so it depends upon the ith coordinate, and then you just go over all the coordinates in the setting which are different, and you take a weighted sum. So this gives a matrix, square matrix with zero diagonal, and the claim was, so yeah, so this side we some error last time when I was talking about it. It's like 1 minus the operator normal, 2 normal matrix times t squared by 2 times summation c squared. So c so your constitutional elliptic function. So this is a similar kind of condition as the usual boundary differences or McDiarmid type inequality. So the difference on the ith coordinates, you know, the way it's c, the difference is ci is the elliptic function on the ith coordinate. And for such functions, so you have essentially the same kind of thing, except that you will get a loss. So you get 1 minus the operator normal. So it does recover, by the way, the usual boundary difference inequality. So why does it recover that? Just recap.
That one was for independent.
Yes.
Yeah. So then in that case, operator A would be 0. Right?
Yeah. In that case, A is the 0 bit. When the U is the product distribution, A is 0. Because the total variation distance is 0. I mean, no matter what the difference is, these are the same. A can be taken to the 0 metric and B usually. Okay. So yeah, so it is a strict generalization in that sense, and yeah, and this you are trying to prove. So we went through it slowly to make sure that it does not look very mysterious, and then we had this natural, I mean, at least in hindsight, natural construction of both the exchangeable pair and the function p. The exchangeable pair is that probably the most natural thing, which is to just do the Gibbs sample. So Gibbs sampling is a reversal Markov chain. So you take x sample from the mean and then take one step of the Gibbs sample. That was what the reversal, the exchangeable pair was. Okay, and we see just about the reversibility of the Gibbs sample that it is exchangeable. Okay, so this was fine. And then we were looking at constructing this P, and based on what we did for the completely independent case, it looks like the natural thing might be to just take fx minus y. That doesn't work. There's some errors. We tried to fix the error, and then that leads to the construction, which was to define p of xy to be the sum of the difference in the averages after k steps overall. So fx minus fy, pf x minus pfy. So you start at x and y, you look at the k step average after x, after starting at x k steps, and you just look at the difference in the average, and you sum it over. And this, we notice it will work provided this average is going to 0, which will happen provided if x itself means 0 and if the Markov chain is path mixing, then p to the k of f will converge to the constant vector, which is every coordinate is the mean of f, and the mean is 0, so it will be the 0. And then therefore this, if the chain is mixing, this will have the right property that, so the error, notice that if you just took k steps, the error is this, but this error will be converging to 0 because of the, because if the chain is possible. And then we had a more simpler way of working with this. So I mean, to do this, if you start looking at difference of expectation, and this is a natural thing when you look at difference in expectation of two variables, it's sort of easier to because so if you have two random variables, so it's sort of easier to construct some kind of coupling of them, so that like most of the time they're equal, so then the distance is 0, so you just have to care about when they're, so by constructing some couplings where they only differ, where they usually are close, you can bound different. So that's the standard. So that's what you are going to do. So you are going to just couple, so find some coupling for which, so yes, for any coupling, this representation will be correct, because no matter which coupling you choose, by definition is the correct coupling, the margins are correct. So each term here would be exactly the pk of it. But if you do a coupling, then these xk and yk would be have a joint distribution, they will not be different, and possibly you can use that as couplings. So that was very good. And there's a natural coupling for any sort of these kind of Markov chains, which is sort of you just try to first couple the, so it's a gift sampler, so you couple which coordinate you're going to update to be the same because they're the same distribution, and then you couple the updates as much as possible. Greedy coupling on that. Okay. So and by the standards of coupling gamma, so there is a coupling which are achieved exactly that they're different only by the probability difference is equal to total variations, and that's the best that you can do with this. So there is such a coupling on every fixing of the rest of the things or every I to use that coupling. So that was a general coupling, and from that we then wanted to understand. So this is all the construction. There are no calculations that happen. So everything was actually pretty standard in these standard tools, putting just put together in a nice way. And now we have to just calculate what this new x is. Fx minus fy is. And this, I think we did one more of this, which is that so that it became like because it's a sum over all k, so this becomes like it's a term by term kind of thing. So it's like fx minus fy expectation of fxk minus fyk under the condition that. So this is the quantity that we, this is of course this has to be done for like yeah, so this is an expectation over xy also in there, but we'll actually the way it will be done is that it's sort of be done in the worst case. So we'll so there's x0 y0. So for any fixed xy, you have to now understand what this number at step k looks like, and it's just a difference of fxk and fy. So okay, so how should we go about that? There's a Markov chain, and there is a coupling between the like steps of Markov. There's a Markov chain for x, there's a Markov chain for y, and there's a coupling between the two. So how do we
actually how many coordinates are different?
Yes, so that seems to be the natural thing, right? So and the reason for that is that this number itself can be bounded. If I look at fxk minus fyk, that itself is bounded nicely in terms of how which coordinates are different. Right? So where? So let me push the absolute value one more level into this. So instead of this, let me just say Okay, so push it more, and and this one, this fxk minus fyk. Now note that. Actually, even for that. So this expectation gets pushed inside xk, yk, ck. So ck is the coupled Markov chain. So the ith coordinate of this is not equal to. Is this clear? So all I'm saying is that, so if I remove the expectation and the fxk minus fyk just by definition c and then you just put it on. X0 y0 is not a random variable right now. I mean, I'm just arbitrary X0 y0. Later on, let me take expectation, but that will actually not be so crucial. Right now, just think of X0 y0 as a fixed. They have a distribution, but what we are more interested in is that after X0 y0 is fixed, what is the distribution? But this is a probability that they are different. So just, I mean, that's just a notation. So this is just. Okay, so this suggests maybe that this is a vector whose evolution we should study. Right? So this is a vector of what dimension? This probability n dimension in the number of bases. So and that is the vector. Okay. So yes, I just follow his notation. So let us define. Lk is a vector, which is okay. So Lk is okay, and yeah, and then and this is the vector whose evolution we're interested in studying. So how does this vector change? Right? And then the error would just be the n product of this vector, which is here. C is the expected. So this vector is so then where? So let me just write it like this. So it's C transpose. Okay, where? Okay. Right. So now so yeah, so how do we see how that vector is changing? What goes together? We have two things. One is that we have a coupling, and other thing we know is that there's total variation distance between x, like under some differences and so on. So that's the only two things we have. And so far, not used the coupling works in a certain way. Now we're happy with that. Right? So suppose so now we want to.
Okay. So LKI is the probability where xk plus 1. So let me just keep, so now these random variables are well defined, right? Xk plus 1, like, so I will not stop writing them. Okay. So the probability that xk plus 1 I is not equal to yk plus 1. Okay. That's what it is.
Okay, so. Sorry? Okay, plus.
Yeah, k plus 1. Yeah. Okay. So now the natural thing to do is a Markov chain. So what's the natural thing to do?
Take one step.
Condition on the previous step and see what happens. Okay. That's the. So which is the expectation of the probability that xk plus 1 I is not equal to yk plus 1 conditioned on xk yk. So the expectation is now over what? Over xk yk. So now, but now what is, if you condition on xk yk, we know exactly how xk plus 1 yk plus 1 is generated, right? How are they generated? You take the same coordinate in xk yk, both the same one, and I mean both coordinates, same coordinate in both of them, and then update it based on the corresponding values. And now to understand why will the I thing be different or not? Okay. So now, so what is this probability? There are two cases, right? Either you pick the I coordinate or not. If you pick the I, if you do not pick the I coordinate, then what happens?
Then it will be the same. And it is same with the same as previous.
Yes.
They were different before they were continuing.
Yeah. So this is equal to okay. So if I is not chosen, if I is chosen, then what it will be?
Then it will be total
Total relation distance between the two plus yes. So this one and that, what is the other distribution?
same for Y.
Okay, but that's not very useful so far. What do we do now?
So we have bound the total relations.
Yes, we have bound the relation in terms only of this vector, the difference vector, right? And then yeah, LK will come when we take expectation. So this, which is less than 1 minus 1 over n. Plus 1 over n summation j going from 1 to n aij I x k j is not equal to. So this, so second step uses the property of U. Okay, first is an equality, second uses. Now we can take expectation. Now when you take expectation of this, the expectation of each of these is the corresponding entry of L. Of L. Okay. Yeah. So taking expectation. Plus what? What is the other term?
1 over 8 times.
Sorry. So it's the ith row of Pi, and or in other words, it's like I multiply A with the and take I.
Okay, and then take that.
Yeah. So okay. So this is for every I. So then, so entry wise, Lk plus 1 is less than 1 minus 1 over n I plus 1 over n A. So let's define, so which is equal to I minus 1 minus I minus 1 minus minus 1 over n I minus A, which is equal to B. B is defined to be okay. So notice that note that all entries of B are non-negative. Yeah, why is that?
Entries of A are also not negative.
Entries of A are non-negative, but that does not mean the entries of B. Actually, no, actually, as you say, is just enough. Yeah. I was thinking that maybe you already need that A is of the small amount, but that's something. Yeah. So B are non-negative because so this means that all of these guys are non-negative. All entries of so. So if you get some bound on the like, so yeah. So what the point is? So like what I would want to say that B has some B's are contraction. So the norm is contracting, and so all the entries will also be smaller than norm. I think it sounds like, but just keep track of it. Yeah. Okay. So now yeah. So now let's so now we are in good shape more or less. So we just so strong. Making sure anything is ready. So I'm looking at so what's the so if the operator norm of A was something, What's the operator norm of B? So this is I think I need the
Somebody's trying to
yeah. So yeah. So I want yeah. So this like the operator norm of so. Okay. So then we just trying to put okay. So this is clear. So yeah, so that is just a timing but I was thinking of something more complicated. But yeah, this is just so you take any vector, any unit vector v, multiply it here. This is just a scaling, so that is scales operator. So the operator, the norm is that. In fact, what I wanted to say is actually equal, but yes, that's probably it's not symmetric. This may cause. Actually, yeah, actually, it's fine. It's fine. And because singular values will also not yeah. Yeah, in fact, it's equal. But yeah, we won't need
A commutes. Because I and A commutes.
no, commute is not the point. The point is,
I mean, you can just say,
actually, it's not.
take norm of BU.
Huh?
You say, you take any unit vector U.
Yeah.
And you say norm of BU versus norm of 1 and I plus 1 and A times. Which will just be. But
No, that's right. It's not clear. It's equal. Yeah, yeah. The singular values may not match up. Yeah, but at least it's less than this, and this is the only side. Yeah. Oh, okay. Yeah. So yeah. Sorry about that confusion. This is fine, and this is all green, and yeah, the other side can be. It's not symmetric. If it's symmetric, everything is fine. But you know. Okay. Yeah, and we don't want to assume symmetry because the what effect I has on J can potentially become what J has on I. So we don't want to use. And yeah, we won't need it. Yeah. Okay. So but we have this, and this is less than one. If A has norm less than one, B also has. So if A is a contraction, B also contraction. So that is. So I mean, anyway, our whole thing is in this is in this. I mean, our whole result only makes sense under this assumption. And so therefore, and then in that case, this also is strictly less than. Okay, but now we are in good shape. So let's just see what is going on. So this is, but I mean, like the way we wrote it, this LK is also a function of the x0 y0, right? And but for any x0 y0, it is decaying like this. Yeah, like the norms are decaying, will be decaying exponentially, but the exponent depending possibly upon it. So yeah, so this notation will become so big cumbersome, but yeah. So what was it? So it was. Right? That's the definition. A sample x condition on the first one. So far, we have conditions both x0, y0, but that's not a problem. This is just going to average over that, right? So, yeah, so let me just see. So let me just keep, I mean, because really it's not just this, right? I mean, you have to sample x0, y0 from D and then the coupling also. So just become two conversions. So that's the distribution. So the x has been, I guess, because yeah, it will look even more cumbersome now. But I just want to write it like this, that x0, y0, given x0. So let's say equal to x, y0 equal to y, times the probability that y0 equal to y, given x0 equal to x. Okay. By the Markovian property. So the Markovian property is important. Like once I sample y0, the rest of it is going to depend upon the y0. So and
Summation over bias.
yeah, so there's summation of that. Yeah. Summation over all the possible states. But how many such states are there? So y0 can differ from x0 in how many places? Just one, yeah, and yeah, so that will be that. So, but let's worry about all. So it's, but I mean, the point that mostly it's the same events. Only one coordinate can differ. So, but let's just see, okay, maybe yeah, let's just keep it. So and now note that maybe let's do that because that's a simplified thing. So note that y that probability y is equal to y given x0 equal to x is non-zero only when x and y differ on at most one coordinate. Okay. Say, let's just see. So if they don't differ, what happens then?
Yes, there is some problem.
Yeah, but then this thing is zero.
Right.
So then every time if x0 and y don't differ, then this thing is zero. So that event we don't have to worry about. Right? That doesn't contribute into the sum. Only those events contribute when they do differ. And when they differ, they will differ on exactly one coordinate. Okay. Say the ith coordinate. That I of course is a random coordinate, and it's so I is random and depends upon x.
Independent of the sample random.
What?
Isn't it independent of x?
Oh yeah. It doesn't really depend on. I mean, it depends upon it in the sense that the probability that you become equal. I mean, yeah, like I might not exist. In the sense that I mean, that contribution might be zero.
So the probability of y0 equals y may depend upon.
Yes, the probability can depend, but yeah. So I say, but let me just say I is random. I mean, the point is that all I want to say is that in the end we will be just dealing with that this number will essentially be a constant for PIs, and everything will come here, and we just do the worst case form there.
So this property actually will play no role. Just some only role it's playing is that it's non-zero only when they require one coordinate. So this number is exactly one of the six. So, okay, this is a bit. It's clear what I'm saying, and okay. So we're not wasting so much time. So but it's fine. So basically, all I'm saying is that like because everything is being averaged over, already look at the worst case. In the worst case, what? So what is the worst case of x0, y0? It will be some CI here. And then of course, whatever CI it is, that's where x0 and y0 differ. So y would be something which is different from x, but only on the right side. And we take the max over all of these. And this mu x is whatever this is going to be an average over all of these. Actually, there's no max over x. X is anyway fixed straight. So okay. So I just want to make sure that like everyone is agreed that there's no cheating going on here. There's an average and we're just taking the maximum of the things that are being averaged. But now we are in good shape. I mean, yeah. So now what do we do? This we know what to count it.
Is bounded by the
Of what? Of LK plus one, whatever, right? So actually, what did we do? We proved that it's like C transpose something. Right? So it's C. Yeah. Yes, so this now it becomes like a linear algebra exercise. So we this is less previous for any. But this LK itself is a function of this XY, right? But what is that function? And so because everything is non-negative, is C transpose. So this is where I'm using all the non-negativity. Of C L D.
Okay. The L0 of xy, but what is the L0 of xy?
Just
Is the condition expectation of this vector where this is they're different. So it's a vector which is one, and just exactly one. Well, if it is zero, then it is zero. But if they differ at one point, so it's exactly the indicator of the ideal. So it's yeah. Okay. And so nu x is less than half max over I summation k going from 0 to infinity of Ci C transpose Bk Ei. That's correct. Okay. It's absolute value. Okay. Yeah, times this. So this was when they declared direct column, but this is the max over I. Yeah. So yeah, okay. So now how do we bound this? So let's just think. So this is like yeah, so I want to say that this is okay. So this is some number. I want to bound it in terms of the correct norms and so on. So this I want to bound by some constant. Right? So and it is clear now that it's bound by constant provided p is because of geometry. It's just the question of what's the right one. So the simplest way to do this is to say that you just take the two norm, right? And okay. And then it will be the operator norm of C, and yeah, which is less than x over I Ci times the yes, is it? I'm just wondering if that's the best way, but let's see. So should I just check this? What's the correct thing? So if I do it this way, then it will be max Ci, the norm of oh, okay. This is the thing. Yeah. So it's max I Ci times k going from 0 to infinity. This is the 2 norm of C times the 2 norm of P to the K. Right? Yes, right. So the 2 norm. So think of this vector and this vector. So this is the norm one vector. This is at most. Why is this? The operator norm of P to the K is at most. Yeah, that's the and yeah, so this is what we have. This sums up to what? So this is a geometric series, right? So this is equal to max I Vi C2 and yeah, I'm guessing I'm going to somehow miss a factor of n somewhere. That's what I'm worried about. Nu times
the one minus norm B.
yeah.
Norm of B is like
Yeah, and this
1 hour, so 1 minus normal P will be like 1 hour and 10s normal performance.
Yeah,
I think this is a factor of half.
yeah, there's a factor of half also. Mhm. Yeah, okay, just 1 second. I might have just misapplied some inequality. Let me check this. Yeah, this is something that I'm just. You just check that this is. If there might be some factors I have bundled up somewhere. Let me just check. Oh, okay. Yeah, I think the maximum that I did was a mistake. Yeah, so that's the thing. So it's not just yeah. So the probability that I happens is 1/n. So yes, we have to be slightly more careful there. Let me just make sure that I. Yeah, so the probability that they differ on the ith coordinate is exactly 1/n. So it's not actually a map; it's actually an average. So let me just take it.
Max over Y I can put, but
Yeah.
I should take that.
Yeah, that we don't want to use that. That's so no, that is non-linear coordinates, there's I coordinate. But then we get it. So yeah. Zero to infinity. And no, it's not and Okay. You go over all the take that, and then for that take the maximum. By what we did was also right, but weaker than what we can. So now yes, sorry about this confusion. So now we can.
This the stop half is just fine. This
Yeah, we just have to slightly change it. Oh, this one. So yeah, so for fixed xy says that no, not for fixed, yeah, fixed y says xy is not equal to y, x is not equal to y. This is what we have. So new x is now less than this. Is not max, but half. I going from 1 to n. Yeah. So, but this now just becomes ci, right? So that's the point. Yeah.
CI times CI is CI. The CI summation I CI times CI is
Okay. So it's 1 by 2n. But that is less than the norm of. And yeah, that's it. So then you plug this into the formula. This is a c, and so you get e squared by 2c. And e squared by 2c, which is exactly. Yeah, I think so. Yeah, so it doesn't. So there was one more which is added up. Yeah, there's no T. That's not 2 here. That's. Okay, so there is one more remaining thing. It's as well, this took longer than I thought. But there's one more remaining thing which is to do the proof of the main lemma. Yeah, that what we wrote is also true, but something stronger. Okay. So yeah, so just to prove the main lemma. But before that, let's just make sure that what is this thing, right? So what is saying to so it's getting concentration, provided the weak dependency is measured in this Toprusian type. So this A is often is related to something called a Toprusian metric or the influence metric. It's like basically saying how much influence I coordinate has on the J coordinate. Or the Aij is like how much influence the J coordinate has on the I. So there, yeah, I'm going too slow. So there are two things I want to do. One is to do one example of this, and the other one was to finish the proof of the main lemma. Maybe the proof of the main lemma I put in the homework, and let's do is some example, one example on the 20 minutes. So
So let's do something of the following. So let's to see how. Seven, eight, for example. So let us consider the following thing. So, so suppose that G equals V is a graph of is a graph of maximum degree less than delta. Okay, and consider the following distribution. Independent sets. So independent are also called stable sets of G. So these are sets of vertices so that no two of them are reduced. Mu of I is proportional to lambda. Oh, sorry. Yeah. Okay. So now, let's see if this has some weak dependence. Right. So, in fact, if you notice, so sort of the weak dependence and the coupling could go together, right? I mean, if you could construct the coupling which has the right thing, that also shows the weak dependence. So that's, I mean, they go hand in. It's the same because total relation is like you found a coupling in which they become equal. The total relation has to be less than the duality what it goes. Total relation is the best possible outcome. So any coupling, whatever it achieves there. So if you have a coupling, which the probability that the two are unequal is something, total relation has to be at most high. The best one will be equal. Okay, so yes, so basically, yeah, so what I am asking is how do you come with some inequality of that kind, that influence matrix type inequality? Is there a nice candidate? First of all, can you tell me a comment to that matrix have to be zero?
So any adjacent things
Have to be zero.
So
Adjacent things are mirrored. Like if some vertex is in the independent set, neighbors cannot be. This is very high degree. Extremely high dependence. But yeah, but you're close.
so you're
So we're going to consider matrix AIJ, right? Which is influence the vertex G1. And what was the setup? What was the setting? You're looking at xi when everything except the I thing is fixed, and yi when everything is I thing, and their difference. So I'm saying that if everything is fixed. So basically, I'm saying that some entries of AIJ you can just say have to be zero. Yes, the structure of it. So let's think, suppose lambda equal to 1, uniform distribution, something like that. What's the most natural thing? Natural, yes.
So you have a vertex. Say
Coordinates, okay. So what is the setup? So you can think of it as a Bernoulli random variability vertex. Is one vertex only the vertex. Yes, and so the n of them.
and that's all. So that's the setup. So to maybe just let me write that. So to put it in the framework, we consider X taking values in 0, 1 omega such that mu x is equal to 0 if x equal to x equal to 1 for some UV in E and proportional to lambda to the power the number of x. Otherwise, proportional in the sense that okay, you sum it up and divide by some positive number, then it becomes 1. Yeah, so now, so what you want to do is you want to so first question is which entries of A we can say diagonal are anyway 0 by definition.
I and J are belonging to different connected components and should be.
Okay, good. Yeah, certainly that's a good done. Because that. But notice that this A is after conditioning also. That is actually true even in the general, like even if I don't do any conditioning, still I and J. And of course, eventually after conditioning also. But now we are doing some conditioning. Maybe that.
It's actually any non-neighbor.
Yes. So if you think about it, any two non-neighbors, if I and J are not neighbors, Pij must be 0. It requires a little bit of thinking or maybe some calculation. Point that this is the so-called Gibbs distribution. It's factorizing over edges and vertices. Such things have the property that if you take any two sets S and T, this is the more general property. If you take any sets S and T, and if there's some other set U that disconnects S, the vertex separated between, so any path from S to T has to go through U, then condition on U, S and T becomes bigger. Here your condition on everything, so you come independent of everything except everything. So which entries are from?
There's a fact that it only depends on the size of the entity.
What?
So, what kind of distributions have this property?
No, this property it only depends on the following thing. So you can define on every edge a function and every vertex a function, and these functions can be different on different edges. And then each function looks at the values of the two, like whatever on the edges it looks like on the, and then you sum it up. And then you take exponential.
So on each edge you have a function, right? And on each
vertex also you have
a random function.
Each vertex you have so the random variable sits on the vertex.
Yeah.
So random variables will always sit in the vertex of the graph. And now to come to the distribution, you have these functions. And these functions are local in the sense that each function, so you can look at so the function, what can they do? So suppose their only function can look only at the, so each function can look at one vertex, and then you are summing over these functions and taking exponential. That is what.
So that is your
What kind of distribution does that mean? So I'm looking at distribution of the following class. I have I have these random variables sitting on them, and the distribution will be of the following class. There will be some deterministic function, which is each function is sitting at one vertex.
probability of x taking this values will be
Proportional to exponential of some.
instead of this one.
Yeah. So what does that mean?
It's gives
No, even more. It's a product distribution.
right.
Yeah, it's a product distribution. Like the variables are independent. Now we are putting in some dependency. How? So now we have one function that's on each edge. And that function can look at the two endpoints and then take its value. And we sum those things also. Now they are not independent. Now, I mean, you can take the functions like this can be written down as well.
Yeah.
And it's not independent. Okay. But also this is the Gibbs distribution. And it's easy to show that it has a property that it will have this kind of. Yeah. In fact, it also converts, but the converse requires more things. So it requires it factorize over peaks. That's called the Hammer's peak there. Technically, that converse doesn't apply to independence as it is. But yeah, so like basically the thing is anything with this Markov, so this thing is called spatial Markov property, what we just said, like the previous thing, that if you have three sets S, T, and U, this one, so the T separates S and U, then condition on the random variables in T, S, and U, random variables S and U are independent. That's called the spatial Markov property. Any distribution that satisfies the spatial Markov property in the will factorize. We'll have some kind of use factorization under certain, some small conditions. But I mean, the small conditions, but they don't like the original theorem, they don't apply anything. Very independent is spatially Markov. I mean, just because they produce the Gibbs distribution. So that does not require anything. If you produce the Gibbs factorization, it's actually pretty easy to show that it has spatially Markov. To go from spatially Markov to Gibbs personal. But once you demonstrated the Gibbs factorization, exactly it's a simple calculation to show that it has spatial Markov. Basically, everything is just cancelled. The things that are outside is cancelled. Just write down take a favorite definition of independence. And there will be equality, and the things that are supposed to be problematic is just cancelled out from this. On the equal part. Okay. So yes, so this is an answer to this. But okay, so now the thing remains is what happens on the edges. Yeah. Yes, I didn't give the argument. I'm leaving with that calculation to you. All I'm saying is that that it has this property. So you can prove this more stronger property that the distribution has the following property. That if I look at random variables, so take any partition, not one partition, take any three sets S, T, and U.
Okay, the spatial Markov property is fine.
Yes, I'm saying the spatial Markov immediately.
Yes, that's what.
Yeah, because because just look at this conditional distribution. It does not even depend upon what is happening outside because there is condition on everything there. So in particular, condition on the neighbors. The neighbors separate you from everyone else. So, or another way of doing it. So I have this thing. I fix my value of my neighbors. The other guys can't affect me at all. So I just make them equal. Is make it equal to this. This distribution doesn't change.
But this has to be true for any x and y.
Yes, but let's see. So you have some. So you take your favorite x and y. Okay. Here, there. On the what I'm going to do. So I have this y. Whichever y you give. On this distribution, I'm going to do some survey. I'm going to take all the x's that are not neighbors of y and make them equal to the corresponding y.
But why can you do that?
No, let me suppose I've done that. My claim is that this distribution output is not changed, so not change nothing here. Has this distribution changed?
So sorry, what is the surgery you're doing?
So I take this x,
Yeah.
and on every coordinate which is not a neighbor of I make it equal to y.
Make it equal to the y coordinate.
Yeah, the whatever the corresponding coordinate of y.
Okay.
Does the distribution change? The marginal distribution of y.
Oh, that's the spatial marker.
Yes, because it's independent of those things given. So this has not changed. But here only the terms that survive are the ones that are corresponding. I might as well take my matrix, not have any weight there. So the terms that correspond to non-neighbors are anywhere here because this means.
Oh. Well, non-neighbors. Because observation is that non-neighbors don't affect the condition distribution.
Condition on the neighbors. If all the neighbors are conditioned on, then non-neighbors are not.
You can choose your preference.
Yes. Because of that. Okay. It's a slightly it's not a complete trivial point, but it's something. Okay, so 5 minutes left. Okay, so now what's the rest of the other entries?
There is an assumption, right?
What?
Was it a sorry?
No, Gibson. Yeah, I mean, like you can write. So what did I say? What does Gibson mean?
Okay,
This potential factor. This is
so
it is the sort of more or less clearly has.
yeah. So you okay.
Yeah.
It's an assumption, right?
It's not an assumption. I mean, like I put a special description, like it's like some distribution on independent sets. The independent set property of this form.
Oh.
I mean, of course, there's some way to become infinity and all that, but that you can handle. So whatever proof you will write for the independence or not general Gibbs things will also work. So the special marker I will prove, and I'm saying it will basically the proof will boil down to 5 this loose space. So the potentials are infinite because you have zero property, but that will not matter. Yes. Let me just call it spatially Markov because that is the really important point. Also Gibbsian modulo one technicality, which is that some potential are infinite because some things are just not allowed. Some things if they happen, you have to put probability 0. But that's not going to be a problem for this case. Okay, but what are the other entries? There are things.
That's simple purpose.
Totally like neighbors. Yeah, not yeah. So what's the remaining entry? So maybe let's think of it in terms of the coupling. So we want to couple. So there are these x and y which are different possibly on the neighbors, and we want to couple. Let's forget about the general case. Let's consider the following case where x and y differ on exactly one of the neighbors. If they don't differ, then what happens?
Then you just make it.
Then the distribution is the same, right? So all the others. So then whatever age doesn't matter.
Sorry,
If the name on the neighbors x and y are equal, as we argued, the distribution is the same. So there's no problem. They can be coupled. But they can also be coupled perfectly, and they are because it is essentially. But suppose so we want to look at when x and y are different than neighbors. But let's look at something different. Let's look at something simpler, which is x and y differ on the neighbors only on one neighbor. Just on one neighbor.
So when
can you find a mere coupling? Like a good coupling between these. So that will involve the relations from work. Finding a good coupling.
if the neighbors are if one of the neighbors is different.
Yeah.
Well, the point is you want to work on the total ratio of some arbitrary problem. So if at least one of the neighbor, if at least one of the other neighbors is 1,
Yeah.
then both have to be 0 anyway. So
Yeah, so they're equal. So then the perturbation is 0.
but if everything else is 0, but only these two differ,
Yeah.
one of them is 1, the other one is 0.
Yeah, so then what happens?
Then on this side, this has to be always 0.
Yeah.
And this one will be 1 with probability something like 1 over numbers.
Yeah, so that's proportional to lambda. So it becomes lambda over 1 plus lambda has to be 1 and 1 over 1 plus lambda has to be 0. Right? So the total variation distance is at most lambda over 1 plus lambda. Or yeah, like we just take the difference between the two. So yeah, lambda over 1 plus lambda. That's the. So this is what happens if there's one difference. Now, so the total variation distance. So a simple coupling argument shows that. So everyone gets this argument, right? Because we have produced a coupling in which the probability of them being different is exactly this. Therefore, total variation distance also can get used. In fact, in this case, this is correct. I mean, like it is either 0 if they're like basically as what you said, like there is one guy which is anyway plus on both sides, forces both of them to 0. Or if it's not, then this is direct. So it's correct, equal also.
So look at it.
The coupling is you yes, so it's so either they're both going to be 0, which case there's nothing to do. Otherwise, you have on one side of a variable or only random variable, which is going to be just 0.
Okay, so just want to have one neighbor which is
Different. So on one side it has to be 1, the other side has to be 0. But it is 1, then I is anyway fixed to 0. Because so then it's a fixed Bernoulli. The other Bernoulli, if it is not fixed, if it is fixed, then it is also fixed to 0. It cannot be fixed to 1. And that will happen if there is another neighbor which is 1. But then that neighbor has to be there on both. The only situation is that this neighbor is the only neighbor that is different. All the other neighbors are 0. In that case, this what is the distribution of this vertex? It is lambda over. So it's like it's a Bernoulli parameter lambda over 1 plus lambda. So there is actually no coupling really. It's like equal to equivalent because one side is fixed.
So,
but now yes.
For multiple processes.
Yes, so for multiple level what happens now?
So even if there are a lot of different than many neighbors, as long as if both of these settings have at least one of them is 1, then they will be equal. And if one side is all zeros and the other side has not all zeros, then again you will have the same lambda or whatever.
Yeah. Yeah. So in this case,
I guess
yeah, that's correct. Yeah, so that's
and if both of them are zero, then both will be lambda or one of them, then you can just make it.
right. But okay, good. Yeah, so yeah, so yeah, so they got me somewhere, but it doesn't. Yeah, okay. But okay. So then what's the matrix now?
It's lambda or whatever lambda times that distance in it.
Yes, good. Yeah, so yeah, so that is correct. So that's what we wanted to do. But I mean, I wanted to do one more thing which is slightly instructive, but it's not. It will show up very soon though. So let's wait for that. So, but then, so this will work even for. So we get that Aij is equal to lambda over 1 plus lambda if I is a neighbor of J, 0 otherwise. Okay, good. So now we have to compute this norm of this norms. So how do we do that? So let me not do this. Let me save. So but at least look at something. The row sum. This is like what? So row sum is like 1 to infinity. So if you think about it, because the one ball, the norm one ball has only like the vertex here. So you just need to check. You just need to look at the actually no, it's 1 to 1. So suppose I want to complete one. So forget about the 2 to 1. Suppose I want to complete the 1 to 1 now. Let us see what is the 1 to 1. The 1 to 1 now. For the 1 to 1 now, because the one ball is a vertex, it has vertices. It has just n vertices, 2 n vertices, one quantity. So because these are convex objects, this is a convex function. I just need to see what is the matrix A doing on each of these corners. Each of these corners, it just reproduces the column, maybe with sign. So that, and these are all non-negative entries. So if you think about the 1 to 1 norm, is just the maximum L1 norm of the columns. Because each coordinate gives one of the columns, you just take the maximum of those. So that is at most lambda delta times 1 plus lambda, right? Okay. What is the infinity to infinity now?
Lambda.
Sorry. Yeah. So the infinity to infinity now, again, there are these. So the infinity to infinity now, there are two ways to do it, but you find that it's a 1 to 1 of the transpose matrix. It's actually the maximum row sum. So like yeah, this was so what you can argue to yourself that the infinity to infinity norm will actually be the 1 to 1 normal transpose matrix. This is especially a more general thing, which is that the P to Q norm will be the if you take a transform, it's not P to P, it will be the Holder conjugate of P. And the reason that happens is because the Holder because the inner product of two vectors that most the P norm times Q norm by P and Q are Holder conjugate. So when you transpose, you change both the sides to the Holder conjugate. So there's only one case when what's the one case where you take a transpose and the norm remains the same? Two, because the Holder conjugate of 2 is but anyway, I mean all this is after nothing, but you can also do it by hand. It's the same way I did this one. Just use the fact the infinity norm is the dual norm, the one norm. Right? Yeah. So in the sense that yeah. So by the two number vector is the maximum inner product you can get over all two norm unit vectors. Right? Similarly, so the two norm is its own dual. But for the infinity norm, the parts of duals have to again the Holder conjugate is the dual, and that's in fact that's what the Holder's inequality says, because there's also an equality thing that with equality you can make something else. So that basically tells that equality happens when you are in parallel. So the Holder's inequality basically tells you that the infinity norm is the dual norm, which is the same thing as what it is. So this will become the maximum rows. Yeah, because the degrees are the same, so these are not symmetric, but it still is the same. And now this maybe requires a little bit more work, and it's again a special case of a more general thing, actually a very nice kind of thing. But this special case can be proved completely elementally just by using Cauchy first. That the 2 to 2 norm is less than the square root of these two things. This you can just use through using these two factors. It requires some 2-3 like Cauchy course, but yeah. So this is also less than. But yeah, but this is also a special case of something nicer. It's called interpolation. But you can do it more than. Yeah, you can do. Yeah, so this one you can do it. The other things require more work. I think called trees interpolation. But yeah, we can check. But yeah, this one you can just do in like elementary. You can just write out. A weak or arbitrary vector B and use both of these things.
So what is the general? So if it is
Yeah, I don't remember.
P to G, then it is square root of.
So basically something like that. It's log convex. So operator norms are. So as a function of 1 over P. So if you think of it as the operator norm of A, the PF norm of A, P to P norm of A, as a function of 1 over P, then it is log convex.
Oh, okay.
Which is what this is. 0 to 1. Yeah. So this becomes like, so this is 0, this is 1, this is 1/2 log is 1. So this says that if yeah, so what does it say? I wrote something that I'm not here. But yeah, so this is lambda delta 1 over lambda. And so if this is strictly less than 1. So concentration for mu, if lambda less than right. And okay, so what was the other thing that caught me? But yeah, so what I was saying is like, yeah, so you could do that coupling argument so that we don't immediately jump to this, which is what we needed. But if you just think about it more, you can convert this coupling argument via something called path coupling into a proof of the mixing time for the Markov chain also. Sort of implicit in all these things. And so you get the Markov chain, the course Markov chain reconstruct that you consider the proof there also mixes fast exactly under at least in this condition. By now it is known that Markov chain actually mixes fast for a slightly longer range, so it's known that it mixes up to something called lambda critical of t, which is more like e to the power of e over this rather than 1 over this. That is tight because beyond that the sampling problem becomes NP hard. I don't know if the concentration result goes all the way to that. Maybe now it is known. Yeah, so that may be something to check. That I mean, this version of the concentration result doesn't go through, but maybe via some blocks over that type things, maybe by now it's known. But that those will be very different results. So proving it via this simple thing might also be something interesting. Basically, these things correspond to something called the uniqueness. So on the tree, if you look at the infinite tree of the same degree, then under this condition, like correlations decay exponentially fast in some precise way. Actually, that condition keeps holding up till this other threshold that I was talking about, and it stops holding just beyond that threshold, and that's what causes the hardness. That hardness of that phenomenon of the tree is what causes hardness in general graph. And roughly at the algorithmic side also, the easiness of the decay on the tree is what causes algorithms. And here it was very nice because it was all just one level. There it was some slightly more global arguments, but yeah, but it has a nice connection. So if you read Chatty's paper, it does something. We apply it to a more complicated model, colorings, and there the situation is much more open. So this argument, if you do it for colorings, so colorings exactly what it sounds like. You have two colors, the graph will get more deep. This argument, you will do the same kind of thing. You will find that you need Q to be at least 2 delta plus 1. 2 delta plus 1. 2 times the delta plus 1.
You want to color it?
No, so the thing is you look at the uniform distribution of all proper colorings. So which means that no two adjacent words are the same color. So if you do the same calculation for that model, like we ended up with this condition, your lambda less than 1, you will end up with Q bigger than 2 delta plus 1. And that chain, so again you have a corresponding number of chains, one that also mixes fast under that condition. That chain is known to mix fast for actually slightly lower via indirect, like 11/6 data. Recently, there's a tool which show that it works. It mixes fast on even under like Q bigger than delta plus some small number, but the graph has to have some like gut condition, not a small cycles. But getting it all the way down, the conditions should be good all the way down to delta plus 1. Yeah, and I think the concentration of this may also not be right. Okay, so let's stop here. Yeah.